In this module, we're going to look at how to work with databases and database storage. We're going to start off by talking about how databases are stored in a SQL Server environment. We're going to talk about data files. We're going to talk about log files. Then we're going to look at how to manage the storage for these databases. We're going to start off by first looking at managing storage for system databases, how to move the storage for system databases, what the system databases are. Then we're going to look at how to manage the storage for user databases. Again, how to do the different movement of files, how to manage the data files, how to add secondary data files. Then we'll look at how to move and copy database files. And we'll look at the process that's involved in the moving and copying of user database files as well as system database files. And then lastly, we'll talk about the buffer pool extensions, what they are, how we enable and configure buffer pool extensions, and how we can disable the buffer pool extensions. So as previously mentioned, when we look at how SQL Server stores data, what we have are several files. We have primary and secondary data files that we have right here, and these are going to be actually what creates the data that's going to be stored to read the data later on. And this information is actually broken up into pages, right? So we have right here 8K pages. So a page stores data, and it can store up to 8K. If you do the math, 8K is 8192. There's overhead for managing the environment. So we get a little bit over about 8,060 bytes that we can store on a page. This number is significant because you can't have a row that's larger than a page. So that becomes very significant. When SQL goes to allocate space, it's going to allocate the space based on extents. And there's eight pages in an extent. So that's 64K. So SQL is going to allocate space for that environment for objects at 64K at a time. Now, when you first create an object, SQL is not going to create 64K just for one 1K object. It'll do what's called a mixed extent. Once we fill up enough data for that extent, it becomes an extent just for that type of object. When we make changes in SQL Server, the changes are actually technically written into memory first. So the data page is brought in to the memory area, and at the same time, you're going to see a modification get written to the transaction log. So that modification is going to be recorded in the transaction log. When the transaction completes, the change is written from the memory environment here into the appropriate database file. Now, whether that database file is the primary or the secondary, it depends on how we've set up the data files and where we've stored the objects. At the same time, that change is going to be recorded as completed or committed, if you will, in the transaction log, so that is completely marked as completed, and we can now read that data from the database. In the time it takes for the transaction to start and before the transaction finishes, what you end up with is something called a dirty page. So when the page that is found that the data is on is read into the memory area up here during the modification process, that's referred to as a dirty page. So it doesn't read that data while the transaction is completing until it's marked as committed in the transaction log. There are ways to control that. We can set up processes where we allow dirty reads, but as a general rule, we don't allow those dirty read processes. So when you're creating your databases, when you're designing your databases, you need to take into account how many of these pages it's going to take to create the object. That will dictate how big these files are going to need to be to hold all of the objects for your database. So when we start to look at the storage options that we have for our databases, one of the things you have to take into consideration is what types of disk storage are you going to use, and how are you going to implement the storage locations for your databases. Now we have three different options here that they talk about. Now it's important to note we're not making any distinctions here between spinning hard drives and solid state drives. We're just talking about how the drives are made available to the SQL Server environment. So we have our direct attached storage, commonly referred to as DAS, D-A-S. These are connected directly to the system. Now, oftentimes they're going to be connected by an internal controller within the server. And they mention here a RAID controller. It all depends on whether you're going to implement RAID or not. But most server class systems today have RAID controllers in it. Heck, many desktops have RAID controllers in them now. So these are connected directly by a controller in the system or directly attached to the system via an external enclosure. The big advantage of direct attached storage, cheap. I mean, they're relatively inexpensive to implement. They allow you to manage it directly with the system. The disadvantage is oftentimes speed of the controllers, and oftentimes they're limited in the number of drives that you can attach because they only have so much space in the enclosures. Storage area networks, the disks are connected over a network, sometimes through a dedicated adapter, that would be fiber channel storage area networks, sometimes over generic networking environments, iSCSI. With those types of environments, all we really need is a network adapter. We should have two for redundancy and fault tolerance. And the advantage is that this storage can be anywhere. What it does limit you, though, is if you have a problem with the connection between the system and the storage environment, you lose access to that data. So you have to implement some methodology for providing fault tolerance and redundancy for the connections. The last option they mentioned here is a new concept that Microsoft introduced in Windows Server 2008 R2, and it's called storage pools. And what storage pools allow us to do is take different types of disks from different locations and different connections and bring them together as a single offered your book list commodity. So what it lets us do is we can take solid state drives, we can take spinning drives, we can take network attached drives, we can take SAN drives for that matter, that have been allocated through one server and then make them available to a service or a component without the overhead of the whole SAN environment and without the cost of the SAN environment. So in other environments we talked about JBODs, just a bunch of disks. Well, instead of having a JBOD configuration, we can simply put them together as a presented storage system combining different components. In addition, we also have the ability to create tiered storage that we're going to see in a demonstration coming up that allows us to say, well, this drive in this pool is an SSD, so it's got a higher tier, and we can put certain types of storage on that tier and other types of storage on the slower drives. So when we talk about RAID, RAID has been around for a very long time. It was implemented in the old mainframe days as ways of providing faster and or reliable storage. It depends on what text you read. Redundant array, disks, those are three of the letters. The I, it depends on what text you read. Originally it was called inexpensive. Now they call it independent. But it really doesn't matter. What you do is you create a series of disks. They're connected to a special controller, a disk controller that's able to handle the writing of the data across the disks. And RAID 0 is oftentimes referred to as striping without parity. The big disadvantage to RAID 0 is there's no fault tolerance. As you can see, we have blocks of data being written. So block A is written to disk 1, then block B is written to disk 2, block C is written to disk 1, block D is written to disk 2, and so on and so forth. The problem you have is if you lose disk 2, all the data is invalid because you're missing every other block of data. The big advantage of RAID 0 is it's extremely fast and extremely efficient. So you get very improved read and write performance from a RAID 0 array, but most people don't use it because of the lack of fault tolerance protection. So we have what's called mirroring, right? RAID 1 is referred to as mirroring. It's important to note, nobody talks about it anymore, but to provide fault tolerance for the failure of the controller itself, you could have multiple controllers, each connected to each disk, and that's referred to as duplexing. So you have two different controllers. When you have a mirror set up, every block is written to each disk. A mirror always has two disks, and the data is written to each disk. If I lose one disk, all of the data is still intact. Mirroring gives us improved read performance, but not really improved write performance. We can read from the two disks simultaneously, but when we go to write our data, it has to actually go to each disk independently. So it really doesn't give us any good performance there. However, it does give us really good fault tolerance. The other drawback to mirroring is it costs me 50% of my storage. So if I have 2 disks and they're each 1 terabyte, I'm losing a terabyte of total storage capacity because I'm using that for my mirror. So then we have RAID 5. Now RAID 5 is referred to as striping with parity, and that little pound sign there is indicating parity data. Now there is technically a RAID 2, a RAID 3, a RAID 4. Those were all developed by IBM. They indicate where the parity data is stored. In most cases, the parity data is stored on a single disk. With RAID 5, the parity data moves. So it moves between the disks, and it allows us to recover in case of a single disk failure. So if I were to write my data, you can see that block A goes on disk 1 and block B goes on disk 2, and then parity data is written on disk 3 to help me recover in case I lose either disk 1 or disk 2. Then the next time we write the stripe, that's called a stripe, we put the parity data on drive 1, then block C on 2 and block D on 3. And you can see what's happening is this parity data is moving among the disks. So if I were to lose disk 2, there's enough parity information between disks 1 and 3 to rebuild block B, block C, block H, and block I so that I don't lose any of my data. One of the problems with striping with parity is it only protects me from a single volume loss. If I lose 2 disks, all my data is toast. So you have to be cautious with that. The other big advantage we have with RAID is we get really, really good read performance. We can actually read from all 3 disks simultaneously. We get some minimal write improvements, more write improvements than we would on a mirror, but this information for the parity data has to be identified and evaluated and determined by the controller, so there's a little overhead in determining what the parity data is and where the parity data needs to go. So to provide a better solution, they came up with RAID 10. Now RAID 10 is actually technically mirroring, so there's your RAID 1. So we're mirroring striping without parity. So we're mirroring this. So what we're doing is we're creating a stripe set without parity. So that's this block here is being done there, and then we're taking that information and we're creating a mirror of it. Again, this is a mirror, so it costs me 50% of my storage, but I get the benefits of the great improved read and write performance for the stripe set without parity, and I get the fault tolerance of the mirror. Now, back to the RAID 5. RAID 5 costs me 1 over the number of drives in my array. So if I have 3 drives in my array, it costs me 33% of my storage for my parity data. If I have 10 drives in my array, it costs me 10% of my storage for my fault tolerance. So that provides a bigger benefit at a lower cost. So after we determine what type of storage we want to use, we then have to decide how large and where we want to place our files to store our databases and our transaction logs. At a minimum, they recommend that you isolate your data files and your transaction log files. What this gives us the ability to do is, in the event that we have a failure, we can recover everything right up to the time of failure if the drives are on different, if the files are on different physical drives, assuming it's a drive failure. So, for example, if I have my database and my transaction log on separate disks, and I lose the disk that has the database on it, if I have a backup of the database, I restore the database, I back up the transaction log with the tail log backup, and that grabs everything in the transaction log, and then I restore it and I haven't lost any data. When you start to look at this, and we'll talk about this again later on, you have to be careful here. A lot of people think that they have a SAN environment, so they have 2 different LUNs, logical units, and they add those LUNs as separate disks, and they put the database on one and the log on the other, and they think they have separated it out. Those LUNs could be coming from anywhere in your SAN, so you really don't know that's not truly physically separating the drives. You may not have any control over that. Also in a RAID environment, the RAID environment protects all the data, not just simply a database and a transaction log. Determine the number and location of your data files. Now there's two different methodologies for this. There's a performance reason and there's a maintenance reason. As admins, you're going to look at the maintenance reason. So what I can do is I can create more smaller files, allocate those into file groups, and then set up file group backups and file group maintenance so that I can use the individual smaller files. An example you're commonly going to see, I have a database that's so large it takes 28 hours to back it up, to do a full backup of the database. And obviously if management says you can't do that, you only have a 4-hour backup window, that's going to be a problem. So if I take that database and I break it up into multiple smaller files and I back up the smaller files at different intervals, I can actually just affect the data in those smaller files, and then when I have a failure of one of the devices that has the file on it, I simply restore that file and the transaction logs associated with it. For developers, more of a performance reason. So what we can do is we can put files on different physical disks and then put different objects on those different files, and we can spread our tables out based on our joins, and when we write our queries, we can write the queries so that the data is being retrieved from different physical disks at the same time. So theoretically, if I'm reading from 3 disks at the same time as opposed to reading everything from 1 disk, theoretically 3 times faster. Again, it's not linear, but that's the general concept behind it. So we can use additional files to spread across storage locations for performance reasons, but we can also use it for maintenance and for backup and restore. Now, the way a transaction log works, it only accesses one file at a time. You can have multiple files, but it's only going to put the data in one file at a time, and then once that file fills up, it'll start to move on to another one. It doesn't work the same way that the database does, where it can actually write different types of objects to different files across the system. So you really don't get a whole lot of benefit out of having multiple files for a transaction log. So when we're starting to look at the database files that we create, we have a couple of properties that we set, and we set the starting size, and then we specify the growth increment, and then we specify the maximum size. And one of the problems that people often do is they don't allocate enough space because they rely on and count on the automatic growth parameter, and that is not a good practice. It would be sort of like trying to put leftover food into a container and taking out a small container and pouring it in and going, all right, that's not big enough, and then grabbing a bigger container and pouring into that and going, okay, that's not big enough, and keep doing that until you find the container that's big enough to hold it. It's a lot of wasted time and a lot of stuff that has to be cleaned up after the fact. So what you want to do is try to estimate the size of the data and log and tempdb sizes that's going to be required prior to actually deploying the database. Now, obviously for things like tempdb, this is going to require some testing up front, and you can't do this unless you've actually done a deployment of some kind. If it's an application that's coming that requires SQL Server for storage, you can check with the vendor and they can tell you what the average size is that they've been dealing with based on conditions within the application itself. What I would suggest you do, especially for database files, is look at how big the individual tables are going to be. And what we do is you look at the definition of the table and you look at the column information for each column in the table, and you look at the size of those columns. And when you have variable length columns, to me it's better to use the max size, because then you'll just maybe have a little bit more space than you need. But they say normally take an average of the different variable length columns. You add all that up, and that's the size of a row for that table. Then you estimate the number of rows that you're going to need for that table, and that's going to tell you how much space you need for that table. You do this for every table that you have, you now know how much space you need for user data. You then add somewhere around 10% for the system tables, and now you know how big of a file you're likely to need for that database. And you can allocate that space up front so that you don't have to worry about growing that every single time new data is added to the database. You can monitor the data and file usage. There's lots of dynamic management views that we can query. There's an old stored procedure we have called SP space used that'll tell us how much space is being consumed by a particular object or in a specific database. You can plan for doing expansion manually. Instead of allowing the auto growth, you can set it up on a specific process. So you might have a database or a table that is receiving data through an import-export operation. So what you can do is, you know when that operation is going to take place. You don't turn the auto growth on until you're going to put the data in. You manually expand it before you start the import operation. It's recommended that you keep auto growth turned on, because if you don't and you run out of space, the database is going to dismount. And you'll see an error in the log to indicate that the database ran out of space. If the transaction log runs out of space, it's going to use whatever transactions it can to write those into the database, and then it's going to dismount the database at that point. So you want to make sure there's auto growth enabled so that you can at least recover from that, but you still need to monitor the process and make sure that you have allocated enough space for your data files. So when you set up a SQL Server instance, the database engine, you're going to have 5 system databases. There could be some other system databases depending on other roles that we implement, but we're talking about the database engine now. So when we do the database engine, you have the master. The master stores all system level configuration data. We've talked about the master many times already. That's where your logins are. When you create a database, it actually modifies the master. The master is extremely important to the SQL Server. If the master fails for some reason, all of the SQL Server instance is going to fail. And the master is unique in its movement option. So you can move the master data files to a different location, which we're going to look at coming up, but it's a little bit more difficult than moving any other data files. The MSDB holds all of the SQL Server configuration data for the SQL Server agent. It also stores all of your backup and restore history information. So there's a report that you can see on any database that's going to identify the last time it was backed up, the last time it was restored. That's stored in the MSDB database. The model is a template for all new databases. When we create a SQL Server instance, there's a default configuration of the model. We can edit that. We can modify the model, and every time we create a new user database, it is actually a copy of the model database. So if you want something to appear in all new databases, you modify the model. The tempdb, we don't ever change that. Remember, the tempdb gets flushed every single time the SQL Server starts, so there's no reason to make changes to the tempdb. We can add files to the tempdb, and we can move the file locations for the tempdb to improve the efficiency of the tempdb environment. Lastly, there's a resource database, and you don't see this. It's a hidden database, but it's there, and it basically is there to hold the sys schema for all of the objects. They've done some research from previous versions, and admins spent too much time in the system tables, and in those tables they could make mistakes which would trash either the entire database or sometimes even the entire server. So by creating a resource database to hold these sys schema objects, it actually minimizes the impact of the administrator intervention. It's also where all of the dynamic management views and dynamic management functions run out of through the sys schema. So when we talk about moving system databases, the way that we do this is different for the master than all of the other system databases. You cannot move the resource database because you can't see it, so there's no way to alter it. But for the MSDB model and tempdb, you would execute the alter database statement using the modify file parameter, and you would modify the logical file name, and you'd modify the path. So you'd specify where the file would exist. After you change that, you would then simply restart the SQL Server service. It would read that configuration data from the master database, and it would now look for those files in the new location. It's important to note that when you are moving these files, you have to restart the SQL Server. So any connections that are on the SQL Server will be dropped when the restart occurs. So you want to try to do this during activity periods when the activity is really, really low, or make sure everybody knows that you have to take the SQL Server down, because that's essentially what you're doing here. You're taking down the instance of the SQL Server. So again, you alter the database, you then stop the SQL Server service, which releases the hold that SQL has on those files. You physically move those files to the new location that you specified in the alter database statement, and then you restart the SQL Server service. For the master, you can't do that because the master is in use, so you can't modify its location. So what you do is you go into the SQL Server Service Manager, and we go into the configuration service, and in that service, there's going to be startup parameters for the instance. And in the startup parameters, there's two values in there. There's a -d, which is the database location, and there's the -l, which is the log location. You modify those startup parameters in the configuration files, and then you stop the SQL Server service. You then move those files to the new location, and then you restart the SQL Server service. If you make a mistake with any of these databases, specifically the the model, the tempdb, or the master, SQL won't start. So if you make a mistake in the path, or you don't move the files correctly, or you fat finger the name, or something like that, you will have a problem restarting the SQL Server service. So the tempdb database is an integral part of the SQL environment. All temporary operations, sorting, filtering, they mention here row versioning, user objects, all of those things are going to be built and managed through the tempdb database. So it's important that this database be as efficient as possible. And so if you have a mixture of types of drives and you have some solid state drives, the SQL Server overall will perform better if the tempdb is using those solid state drives over spinning drives for, say, the data files for user databases. It's truncated, as we've already mentioned, every time the SQL Server restarts. So every time the SQL Server restarts, it does recovery on the system databases, and then it clears the tempdb database, and then it does recovery on all the user databases. So there's no point in actually trying to manipulate the data that's inside the tempdb. However, we can increase the number of files that are used by the tempdb so that it can read from simultaneously multiple files at the same time. And what that will do for us is improve the performance. So we can add additional files, and the recommendation is that you have one file for the tempdb for every core that SQL Server is going to use. They mentioned once you get above 8 cores, you can reduce that ratio, but that's generally what they recommend that you do. In addition, it's recommended that you put this on the fastest I/O storage subsystem that you have in order to improve the performance. In older versions of SQL, they toyed with the idea of giving you the ability to put tempdb in RAM, and while the tempdb became faster, it limited the amount of memory that SQL had overall and actually was detrimental, not a performance improvement. So we can't do that anymore. However, we can put the tempdb on really fast I/O subsystems like solid state drives, and that will greatly improve the overall performance of our SQL Server. In this demonstration, we're going to look at how to move the tempdb files. In this demonstration, we're going to look at how to move the files for the tempdb database. What we're going to do first is we're going to view the location of the tempdb files where they are now. So if we go to our system databases and we click on our tempdb and we go to the properties of our tempdb, on the Files tab, we're going to see that our tempdb files are stored in these locations. So our temp log file, we have these temp options that have been created for us, and if you look, this is the file group that it's on. If we scroll out here to the right, you get to see the actual path, and they're all in the C:\program files Microsoft SQL Server directory, which is the default location because that's where the SQL Server was installed. So now what we're going to do is we're going to go ahead and load in a script, and this script is already created for us for the lab environments and for the demonstration environments. And what this script is going to show us is the transact SQL command that we would use to move the tempdb files. So you can see right here, to move files for any database, you use the alter database statement, use the modify file option, the name of the file that you want to move, and the location that you want it to be in. So again, let's go back over here to the tempdb and go to the properties. So tempdev and templog is what we're going to move. And you can see right here is tempdev all the way at the top, templog is all the way at the bottom. And again, you can see their location, and they're both on the C drive, okay? So now what we're going to do is we're going to highlight this portion of the script, and we're going to execute that, and that's going to move it. Now notice at the end of this, it tells you the new path will be used the next time the database is started. Now the tempdb database, you can't simply stop that database because SQL is using it, it's in use. So what we have to do is we have to restart the SQL Server service in order to have the tempdb use the new location. So if we go into the tempdb properties and we look at the files, you're going to see that they haven't moved, right? They list it there on the T drive, right? So they list that they have been moved, but if we go to the T drive and we look, there are no files there. So some of the things you'll notice with SQL, some of the tools in the Management Studio will show you what the settings are, but not what the current values are. So the current settings are to put this on the T colon location, but since we haven't restarted the SQL Server since the changes were implemented, they haven't taken effect. So we'll click here, and we will restart the SQL Server service. Now in real life, be very cautious about this because this is going to kick anybody out of the SQL Server that's in the server and may cause transactions to be rolled back. So we should implement this setting at low activity periods. So we've already stopped, and now we're doing the start of the SQL Server service. So now if we go back over here to the T drive and we look, there are the files for the tempdb database. So again, remember the process: alter database, the name of the database, move the files, and then you have to restart the database. In this case, because it's the tempdb, we have to restart the SQL Server service. In this demonstration, we got to see how to move the files that are associated with the tempdb database, as well as to create additional files with the tempdb database. So whenever you create a database in SQL Server, it's always a user database. You can't create system databases. There are some options that we can do that will create some system databases. For example, when I turn on replication, that's automatically going to create a distribution database. But that's done through a process, not done because I created the database. So when we create databases, we're creating user databases. We can use the SQL Server Management Studio to do this. And when we do that, we simply go to the Databases node and we click on New Database. So we right-click on Database, we click New Database, and that'll walk us through the process through a wizard to create the database. From there, we can specify the file, we can specify the size, we can specify the physical path to the file, we can specify some options, not a whole lot of the options that we can do. We can also, and what's much more common, to create databases by using the create database statement. The advantage of using the create database statement is I can save the script, and in the event that I have a failure of my master database, I can rebuild my master database, rerun my scripts, adding the for attach at the end of the create database statement, and it simply attaches the files that already exist to the master database. So when we use the create database statement, we specify this on keyword, and then we specify the data file name. Now notice this is the logical name of the file. This is the name that's referenced in the SQL master database, and this is the physical path. We use the MDF extension just because it's a recognized extension for SQL, but this can be anything we want. It's preferred to use MDF. The M stands for primary. I know it's not a P because we don't want to use PDF, right? But that is our primary data file. If we create additional files for the database, the preferred extension we will give it will be NDF, and that stands for secondary data files. We specify the initial size. Now we talked about earlier, this should be realistic to what you expect to be stored in the database based on all the tables. We specify the max size that it can get to, and then we specify the file growth increment. Now the file growth increment in a percentage is going to be the current size of the file. So if the file grows to say 400 meg and I do a 20% growth, that's going to be an 80 meg increment. Then we specify the log. Every single database must have a log file. Even if you're going to later set the database up as read-only, you still must define a log file. You can make it a small log file, but remember, when you go to put your data into the database, it needs to use the transaction log to actually populate the data into the database. So again, we specify the logical name, we specify the physical path, we specify the initial size, we specify the maximum size, and then we specify the growth increment. Now notice here, the growth increment we're using is actually 10 megabytes. So every time the log file runs out of space, it'll increase it by 10 meg at a time. That is a very small increment size. You probably want to make it larger than that, but keeping in mind that we started it off as a 20 meg file, that's a 50% increment. This is most likely going to be too small for the data. But again, these are things you have to plan for when you're using the SQL environment. Also note that all of this is in parentheses, okay? So within the parenthesis names there, and then we have log on, and we have parentheses around that. It's also important to note that we don't have a word in here. We don't have file names, file growth names, or excuse me, file group names. We could create file groups, and you can do that through the SQL Server Management Studio wizard. We could also do it here. This is going to be referred to as the primary file group. We could choose additional file groups. All of the system tables for the database go in the primary file group, and the primary file group is the default location for all objects that we create. We're going to talk about additional files and file groups in a little bit. So once a database is created, there's lots of options we can set on the database. Some of the options they list here are things like in the auto options, we have auto update stats, auto create stats, auto shrink. They recommend you don't turn on auto shrink because you get this problem where it shrinks the database and then it needs space and has to expand it again. They recommend you always leave on auto create stats and auto update stats so that it automatically updates the statistics for efficient use for the query optimizer. We can turn on page verify. Page verify is a replacement for something that used to be called torn page detection, and it identifies the data, and it does check values on each page. A page in a database is 8K, and verifies that the data matches the checksum value that's been created for the page. We specify a recovery model. The three recovery models we have are simple, full, and bulk logged. If you want to be able to back up transaction logs, you need to either be in full or bulk logged. Bulk logged is usually used for bulk operations. Simple recovery model is also referred to oftentimes as truncate log on checkpoint. You can't back up any transaction logs. And then you can define things like the state. This is going to be whether the database is online or offline, whether it's set for read-only, whether it's set for DBO use only. Restricted use is what that's referred to as now. So it allows us to control who's allowed to be in the database. Be careful here because I could use a transact SQL query to set the database to single user mode and then turn around and try to use the management studio to connect to the database, and I can't. And you're going to scratch your head and go, why is this doing this? It's because your transaction in your query is already connected to the database, and now you can't connect to it from any other place. So keep that in mind when you start to look at this. Pick a pattern that you're going to use to manage the environment. But this is how we've talked about this before when we talk about migrating databases, maybe setting it to read-only so no other changes can happen while we're creating a copy of the database on the other instance where it's going to live. In this demonstration, we're going to look at how to create SQL databases. In this demonstration, we're going to look at two different ways to create databases. First, we're going to use the SQL Server Management Studio, and then we're going to use Transact SQL. So from the SQL Server Management Studio, we will click on the Databases node, and in the Databases node, we'll click New Database. We're going to call this database DemoDB1. So we'll put that name in here, And if you scroll out to the right, you'll get to see the actual paths. So what we're going to do first is we're going to browse the path, and we're going to put this on our D drive, demo files mod 04. And then we're going to call the name of the file demodb1. Now remember, this is a logical name, so later when we alter database, if we want to alter the file location, we want to alter the details, we use the logical name of the file. We'll go ahead and change the location of the log file as well. The log file is also going to go on d:\demo files mod 04, and we're going to call the log file demodb1. The file name here is going to be .mdf. The file here is going to be .ldf. It's a very common practice to use MDF for database files and LDF for log files. Notice we could also add additional files to be used. This would allow us to spread data across multiple files. We'll talk about multiple files and file group databases a little bit later on. So we click OK. That creates our database. And if you look, here's demodb1. We have a database. If we come over to our D drive and we look on our D drive and we go to demo files mod 04, there are our two files for our database and our transaction log for demodb1. Now, the second option, we're going to look at how to create a database using Transact SQL. So we're going to create a database called demodb2. Notice first that we are in the master database. When you create databases, you must be in the master database. Then we specify the syntax of on, and we specify where the data file will go, and we specify where the log file will go. It's important to note, we could simply say create database, the name demodb2, and it would automatically create everything with default settings in the default path that's defined in the properties of the SQL Server. In our example, we're going to put demodb2, the data file, on the M drive, data. We're going to call the file demodb2.mdf. The initial size is going to be 100 meg. The max size is going to be 500 meg. The log file is going to be on the L drive, L:logs. It's going to be called demodb2_log, and it's going to have a path to demodb2.ldf. The initial size will be 20 meg, unlimited file growth with file growth of 10 megabytes per option. So this will allow us to create the database, and you can see that we now have the database. And notice, because I did this through Transact SQL, I don't see the database in the database list. So what I have to do is I have to refresh the database list in order to see the new demo database. If I come down in here and I run sphelpdb, it'll show me the properties of that database that was just created. Now let's go back over to the file system. Now notice the size of the LDF and MDF files for demodb1. The default size is 8 meg. Right? That's not going to be enough to hold any data whatsoever. So as soon as I go to put something in, I'm going to have to increase the size. If we look at the M drive and we go to data, there's the MDF that we just created. Notice how it's 100 meg because that's what we said in our script. We told it the initial size was going to be, scroll up a little bit, 100 meg. Right? So that's what it does for us. So if you know what you're going to be using the database for, you can configure it and create it the right size to start with. In this demonstration, we got to see the process for creating SQL databases. We got to see how to do the creation using the SQL Management Studio, as well as how to use the create database statement. So when we're changing options for a database, we use the alter database statement. A couple of notes. One, you have to have certain permissions to run the alter database statement. Number two, some of the settings we can use that we can set on a database can be overridden in a query session. So just keep that in mind. Sometimes we can make a setting on a database that can be overridden by an end user in their query session. But to make changes to the database options, we use alter database, the name of the database. We specify the option using the set parameter. If we wanted to alter the compatibility level of a database, we would say alter database, the name of the database, set compatibility level. Please note that all of these things are going to be based on a name with no spaces, so we have an underscore there, right? But we don't need quotes, right? Because it's a known property. And then we have, in the case of compatibility level, equals, and remember we did this earlier, so SQL 7, SQL 8 is 2000, SQL 2005 is 9, 2008 is 10. So this would be setting the compatibility level of the database to transactions and commands that are compatible with SQL Server 2008. So we can manage the files that are being used by a database. Now remember, when we created a database, we specified logical file names, and then we specified the physical path. So what we can do is we can add space to a database either by adding additional database files, again for things like file and file group options, if we're looking at maintenance options, or for performance reasons we would do it for additional types of objects. We can also alter the database and modify the file and specify a new max size for the file, and that increases the size of the file. Or we could alter the actual size of the file. Instead of allowing the auto growth to happen, we can manually expand the files using the alter database statement. If we want to drop files from a database, the first thing we have to do is make sure there's no data being consumed or used by SQL in those files. So we have to run the dbcc shrink file command with the empty file property. And what that's going to do is empty everything off of that file and move it to other files for the database. It's going to move it to files that are being used by the primary file group. Then we can use the alter database statement to drop the file. So similar to add file, instead we say drop file. When we're removing objects from SQL, the term is drop. When we're deleting rows from a table, it's delete. Then we can shrink databases. Now remember, there's an option to set it up to auto shrink, but that oftentimes doesn't work out well. So instead, what we can do is we can manually shrink a database, and that's just going to shrink the overall size of the database itself. We can specify a target size that we can recover to. A database will never be shrunk smaller than the actual data in it. So no matter what size we put, if we make the size too small, it'll shrink it down to what it can. Chances are it's probably going to increase the next time we try to add data to the database, so be cautious about the shrink database command. If we want to shrink a file, we can actually tell it a specific file. And again, oftentimes this is because we're getting ready to remove the file, so we're going to use the empty file parameter on the dbcc shrink file. If we want to simply just clear out the unused portion of data from a file, we can specify truncate only. And what that's going to do is that's going to reclaim all of the unused space that's allocated to a file. Again, in real life, most likely what's going to happen is that file is going to have to increase as soon as we try to add objects to the database. So be careful about doing too many of these shrink operations unless you've made modifications to the way the data changes, or maybe you've set the database to read only. So we've talked about file groups previously. Now we're going to look in more detail about what they do and how they work. As the name implies, a file group is a group of files, right? It's a group of one or more data files that we allocate. Log files cannot be part of a file group. So notice there's no file group option down there. When we set up a file group, as I mentioned before, when we created the database and we said on and we didn't say anything, any name after that, that's the primary file group. In the old days, we would actually say on primary. We don't say primary anymore. And what we have in this example here is we have a secondary data file and we have a primary data file in the primary file group. And so what it's going to do is it's going to put the data across these files to store the objects in the individual files for the file group. And it's going to spread the data across in a stripe that we normally configured separately in the file system. Here we're actually telling SQL we want to use these individual files for the items. Now, then we've created a custom file group. So we've added a new file group. To that file group, we've added two different files across separate disks. Then when we create objects, we would say create blah, 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 create table, the table definition, and then we'd say on custom FG, and that would create the object on these files in the file group. As an administrator, the reason we would do this is the primary file group is where all the system files are going to go. All the system objects are going to go, all the system tables are going to go. We could then change what's called the default file group so that any new objects get created here in this file group. Then we could set up a backup scheme to back this up more frequently than we back that up. So we can back up just the file group and it'll back up the files in the file group. And then if we have a failure, we can restore just this because this hasn't changed, maybe. We can also put them on separate schedules. So we could set it up to back up one file group on Monday, one on Tuesday, one on Wednesday, one on Thursday. So that's the reason we would do it. Developers will use this method and put one object here and one object there. And notice these are on separate disks so that when they go to retrieve the data, it can read from these disks simultaneously, thereby improving the performance. That is one of the reasons why developers use multiple files and multiple file groups. But what it lets us do is create separate storage entities that are identified to SQL to allow us to store objects, and then we can use those storage locations for better maintenance and for better performance. So there's multiple methods to create a file group. You can use the SQL Server Management Studio. So there's a file groups node for your database, and in that file group node you would click on it and create a new file group. You'd add the files to that file group. You'd specify the size, the increment, and the file increment, and the max size. We can also do it through the Transact SQL. We can do it when we're creating the database. So as part of the create database, we can add file group and then specify a name for the file group, and then we would do it similar to the way we did the primary file group. We would say on, and then we'd specify a name for the file and a path for the file. We can also do it after the fact. We can alter the database and then say add file group, and then we would specify again the same properties for the add file group. Once you create a file group, you're going to want to control where the objects get created. If you don't change the database, if you don't alter the database and modify the file group, then the primary file group becomes the default location when you create an object. So if you don't specify when you create a table, a trigger, a view, it's going to go in the primary file group. This way we can actually tell it to create these objects automatically on a different file group. So we say alter database, modify file group, the name of the file group that we want to become the default, and specify default. It's important to note there's only one default file group. It's either the primary or one of the custom created file groups. If you run this command again, put in a different file group name, that supersedes the other file group as the default. We can also set up file groups as read-only file groups. And one of the reasons we would do this is we have data that doesn't change, that's used as the static or the source environment for data that does change. And so when we set up a file group as read-only, it lets us do a concept that's covered in the admin class about piecemeal restores. And so what it lets us do is back up the read-only group once, then we back up the read-write file groups as they change, and in the event that there's a failure, we can provide access to the database quickly by recovering the read-only file group, and everything is there that was originally there. Now it's not up to date, but people can access that data and use it for decision support and queries while we're recovering the rest of the read-write file groups and the transaction logs associated with them. So after a database is created, if we need to for some reason, we can move the database files. One of the reasons we might want to do this is we might want to move the files because we've added a new drive that's a more efficient drive. We've replaced a drive. We've decided for performance reasons we would prefer to have the file running across a parallel disk so that we can stripe data across the drives. Whatever the case, in order to do this, the first thing you have to do is take the database offline. Nobody can be in the database files while you're trying to move them. It's also important to note that if a database is online, SQL Server locks the files in the file system and there's nothing you can do with them. So what we do is we take the database offline, we physically move the files to a different location, and then we use the alter database statement to modify the file location. We specify the logical name of the file, and then we specify the physical path. All we're doing is changing the pointers that are stored in the master database about this particular database and pointing them to a different location, and then you bring the database back online, and it looks in that new location. If you make a mistake in either the path, or you move them to the wrong place, or for some reason you change the name of them, you can fix that by simply running the alter database statement and put in the correct information so that the master can now find that database. You're going to see this in some of the labs where you're going to see they're going to simulate failures of a database because the files are in the wrong place. So that's the process for moving database files. Again, take the database offline, move the files, and then alter the settings inside the master database to point to the new file location. So if you don't like moving the database using the Transact SQL code, we can use the database copy wizard also to move a database. So you would go into the server, and you can specify the same source and destination servers, or instances as it should say, for the destination, but we can specify this option to move or copy a database to a different instance or to the same instance. You specify whether you want to move or copy it. If you're going to move it, it's going to essentially detach it from the original instance and then reattach it to the new instance. If you copy it, it's going to create a copy of the database. It's important to note that it's simply going to create a script that's going to extract the data out of the current database and copy it over to the new environment. One of the advantages that we have with using the database copy wizard is the ability for it to script the logins that are mapped to the users in the database. That way, if we're attaching this database or copying this database to a new instance, all of the users will be properly mapped to the SQL IDs, and you won't have any orphaned users. You can also choose what other objects to copy. You can choose to copy dependent objects. If there's foreign key constraints between tables in this database that are mapped to other objects, we can actually copy those objects that are dependent objects as well. We can copy jobs that are related to this database. We can copy error messages that are related to this database. So the wizard lets us do a lot of things that we can't do by doing backup and restore or by doing detach and attach options. With the database copy wizard, we can also tell it to create a job that will actually save this and allow us to schedule it for a later time. So we can tell it we want to do this, and we do this during regular business hours, but we want this operation to occur when nobody's there. And we already talked about this. This is one of the ways that we can upgrade SQL servers in a side-by-side upgrade strategy. So another method of moving databases, not really the files so much, but moving databases from one SQL instance to another, is to use the detach and attach options. Now, a couple of notes about this that are kind of important. One, when you detach a database, all you're doing is first you are removing the entry from the master database that this database exists. And when you do that, SQL is releasing its locks on the files that are identified by this database. Once that lock is released in the file system, you can do whatever you want with those files. And that includes copying them or moving them to a different location. And then on the other SQL instance, or the same instance if you want, you can simply create the database using the forAttach parameter that's just going to look for the files and create entries in the master database to point to those files. So again, we can reattach these files to the same instance or to a different instance of SQL Server. This was one of the ways that we could do side-by-side upgrades for SQL servers. It's also potentially useful in disaster recovery scenarios. So you have a SQL server that's died, or you have a SQL server whose master database has died, and for some reason you don't have backups of the master database. If you have documentation, so you've stored all your databases in the same general location, you can go into that location, identify the files that are there for the databases, both the database and the log files, and then use the create database statement for attach, and it will automatically re-enter that information into the master database, thereby recovering the data intact without trying to recreate the files. In this demonstration, we're going to look at how to detach a database and then how to attach a database. In this demonstration, we're going to look at one of the ways that we can get databases from one SQL Server instance to another. In this example, we're going to look at how to detach and attach databases. So you'll notice we have the DemoDB2 database, and if you remember from the previous demonstration, this is going to be on the M drive and the L drive, which is where my M is where my data file is, L is where my log file is. So what I'm going to do is I'm going to right-click on this database, and I'm going to click on Tasks and say Detach. So the detach option is right here at the top. And notice what we're going to tell it to do is we're going to tell it to drop all the current connections, and we're going to tell it to update the stats on the database. Now when we click OK, what's going to happen is the database is going to be offline and nobody's going to be able to connect to it from anywhere, because as far as the SQL Server is concerned, this database no longer exists. So if we refresh, you'll notice that right there it refreshed for us, so DemoDB2 is gone. However, if we go over to the file system and we go to the M drive and we go to data, the files are still here. And again, same thing if we go to the L drive and we go to the log file is still there. So now what we're going to do is we're going to connect to a different instance of the SQL Server, and we're going to connect to the SQL2 instance. And in this instance here, we're going to come into the databases and we're going to say attach database. Now when we go to attach the database, we're going to tell it where the data file is. The details about the log file are actually included in the data file. So when we go to the M drive and we click on data and we pick up the DemoDB2 MDF and click OK, notice how it automatically populates the location of the log file. So when we click OK, what's going to happen is it's going to take all of the data and the log information from the old files and add an entry in the master database on SQL2 to point to DemoDB2, and the DemoDB2 database is now on the SQL2 instance. In this demonstration, we got to see how to detach a database, how to attach the database, as well as how to verify that the attachment took place successfully. So when we talk about the buffer cache extension, what it allows us to do is essentially add some functionality to SQL for performance reasons without actually having to add physical memory. If you remember our discussion earlier, when we have modifications, those modifications have to occur in memory. So we have to bring the page that's being modified into typically memory, okay? But we only have a finite amount of memory. So what the buffer cache extension lets us do is it lets us create the process where the cache is brought in to the page. The page is then brought in to the buffer cache extension, and that allows the data now to be stored on an SSD. When we need that data, these clean pages, and they have to be clean pages, these are unmodified pages of data, when we need to modify that data, instead of having to read the data from this slow disk down here, we can pull the data from over here where we have this much faster extension that's running off of SSDs, and we can bring that data in to the buffer cache, which is then going to allow that modification to occur in memory, and that process then speeds up the updating process because we don't have as many latches where we have to retrieve the data from spinning disks, which are considerably slower, usually about 100 to 1,000 times slower than the SSDs will be. And that's going to give us the ability to speed up the process without having to add physical memory, which is generally going to be considerably more expensive than this SSD concept over here. So if you remember previously, we talked about what the buffer pool is, and it's an area for data to be cached. There's a data cache, there's an object cache, there's a user object cache. But what it lets us do is anytime we make changes to environments or anytime we want to access data from a table, it has to be brought into the data cache in order for us to access that data. Well, the data cache is part of the buffer cache. So in an OLTP environment, what we can do is we can increase the size of this buffer cache even though we don't have any more physical memory to allocate. Physical memory, first and foremost, is limited in its size for most systems, and it's usually very, very expensive to implement, especially on server class systems. What we can do is we can add storage devices and use those storage devices like memory for the buffer cache. Anybody that's played with a feature in Windows that was introduced in Windows Vista called ReadyBoost, this is very much like ReadyBoost. So we add a thumb drive in ReadyBoost, and then we tell it we use that for the page file. And so it's a much faster page file. Well, here we're adding an SSD, and we're allocating that SSD, that solid state drive, which is faster than spinning hard drives, but slower than physical memory, and we're telling it to use it for a specific cache. So in order to do this, you do this in systems that have up to 32 gigabytes of memory. Generally, we do it somewhere between 4 and 10 times the amount of physical memory that's in the system. Obviously, the more memory you have, the smaller the buffer pool extension needs to be. And you would put it on high throughput storage. Now, unfortunately, SQL Server has no way of identifying that, so it won't let you choose that. It won't restrict you to choosing only SSD devices. We could choose a spinning hard drive, and it's going to be done in a demonstration a little bit later on, just so you can see how it works. It will improve performance for read operations, but it won't improve performance for write operations. Remember, the buffer pool is just where we're going to read the data into, and we're going to access the data from that cache. It's not going to improve change writes to the database, and it's not going to improve change writes to the transaction log. And when I say write here, I'm talking about write as in writing data, not permissions. So we're not going to improve those writing operations, all right, because it doesn't, those components are still on the other types of storage. So it doesn't do much for data warehouse workloads. It doesn't do much for OLAP workloads. It doesn't do much for OLTP workloads that have very high write operations. And it really doesn't help much if the SQL Server has more than 64 gig of memory, because there's really no reason at that point to allocate a buffer cache, because there's plenty of memory that can be allocated to the cache, which is going to be faster than the buffer pool extension that we're determining here. So to enable the buffer pool extensions, it's really simple. You alter the server configuration, but unlike previous times where we used spconfigure to make changes, this doesn't require us to reconfigure the server. So we simply say alter server configuration, set buffer pool extension on, and we specify the path to it. You can only have one path to this thing. You specify the path and the size. Now remember, the size here should be between 4 times and 10 times the amount of physical memory in the system. Once we set the buffer pool extension, if we want to alter it in any way, we want to change it, you actually have to disable it. So you say alter server configuration, set buffer pool extension off, and then you have to turn it back on again with either the new size or the new path that you want to use. And there's a bunch of dynamic management views that we're going to look at in the demonstration. It's going to show you how you can tell if the buffer pool extension is being used and what objects are in the buffer pool extension. In this demonstration, we're going to look at how to implement the buffer pool extension. Now, normally in real life, this would be done on a system that had solid state drives. For those of you that might be familiar with a feature that was introduced in Windows Vista called ReadyBoost, it's a similar concept. So what we're doing is we're extending the buffer cache and a pool for the buffer cache by using SSDs. SSDs are considerably faster than spinning hard drives, not quite as fast as internal memory, however, a lot less expensive and a lot easier to implement. So the first thing we want to look at is we'll go to our T drive, and you'll notice on our T drive that we don't have any file called mycache.bpe. We're going to come back to that in just a moment. So now what we're going to do is we're going to run this transact SQL statement here that's going to alter the server configuration. It's going to set the buffer pool extension to on, and it's going to store the buffer cache, the new buffer pool extension, on the T drive in mycache.bpe with an initial size of 10 gig. So when we run that, that's going to enable the buffer cache extensions. So when we go to the buffer pool extension details from the dynamic management view OS buffer pool extensions configuration, we're going to be able to see that the buffer extensions has been enabled, and it's got a file, t:/mycache.bpe, and you'll also know that the current size is 10 gig, which is what we set the initial size to be. If we go over to the T drive again and we look, there's the buffer cache, and you'll notice right there that it is 10 gig in size. Now, if we wanted to see what was being used in the buffer cache, we can select the buffer descriptors, and that will show us the information that is stored in the buffer cache and what's currently using information in the buffer cache. And you'll see over here to the right, just a little bit, is in buffer pool extension. That would tell you if the data was in the buffer cache extension. Right now nothing is in there because all of these were running prior to us implementing the buffer pool extensions and the buffer pool cache. If we were to create some activity in the SQL Server, you would see some things would have gone into the buffer pool extensions. So now what we're going to do is we're going to show how to disable the buffer pool extensions. We will execute this code, and then we will look at the buffer pool extension here, and you'll see that the buffer pool extension is disabled. And what we will also see is if we go to the T drive that the buffer pool extension file has been removed by the SQL Server when we turn off the buffer pool extension and enable the buffer pool cache. In this demonstration, we got to see the process for how to implement and turn on the buffer pool extension, as well as how to verify the buffer pool extension was on, and then how to disable the buffer pool extension. In this lab, you're going to manage database storage. You're going to create databases. We're going to start off first by managing tempdb storage. You're going to add additional files for tempdb. You're going to move the tempdb files. Then you're going to look at how to create databases. You're going to create 2 databases, and you're going to look at managing those database files. And then lastly, you're going to attach a database from an existing file. This lab should take about 45 minutes.